In this video, we'll cover the problem largest component on struct. So here, we'll take in the adjacency list of an undirected graph, and we should return the size of the largest connected component in the graph. And so they have some test cases for us here. Now, the key is that, for this problem, we are given an adjacency list. Oftentimes with other problems, we're going to be given an array that contains a bunch of subarrays, and then we build the adjacency list. But here, we don't have to. Now, if we think of our mental model of our graph, remember there are probably multiple connected components, or at least there can be multiple connected components. And we have to figure out which one is the largest. To do that, obviously, we need to figure out the size of every connected component. This means two things. Number one, we need some entry point into every connected component. We can't magically know what these entry points are, so we're going to check every single node and see if it is the entry point to a new connected component. And number two is that we need some way to find the size of a connected component. And basically what that means is traverse the whole component and count the number of nodes that we encounter. So we could use either a depth first or a breadth first search to do that, or more precisely a depth first or a breadth first traversal. And we'll choose a breadth first traversal for today's video. So we can go ahead and get into coding this. Now, like I said, we're going to want to have all of the nodes here. The way we can get the nodes is just the keys of our adjacency list in this case. So we're just going to do object.keys of our graph. Then we're going to want some information. So we're going to need largest component size, and we'll set that to be 0 as a default. We'll go with that for now. Maybe they want us to use something else for the default, but we'll see. Then we'll iterate through each of our nodes. And what are we going to do for each node? Well, one thing is we might have already kind of visited the component for this node. So we're going to have a visited set. And we'll say if visited has our node, then we can just continue. We don't need to actually check this component again because we've connected it before, because we have checked it before. Other than that, we can say cur component size is going to be we'll have some function get component size, and that's going to take in our starting node and then the graph, and it's going to return a number that is the size of this component, the component that this node is a part of. Then we need to see if that's greater than our current largest component size. So the easiest way to do this is we just set largest component size to be the max of whatever it currently is and this current component size. Then in the end, we want to make sure that we return our largest component size. And I believe that this should be kind of the skeleton outline that we need. Now there's one point I want to mention before we talk about this get component size method or function. Oftentimes, people will put the visited set inside of their traversal, their BFS or DFS, especially BFS, traversal function. And that is completely fine in a lot of cases. It makes sense if you want to have a unique visited set every single time that you are running your BFS. However, in this case, we do not want to have a unique visited set every single time. For example, if we are on the 0 node, we traverse it, and we have also traversed 8, 1, and 5. Then, when we have finished traversing the entire component, we wrap up, we grab our component size, we compare it, and we do our max calculation here. Then we go to the next node, which is a 1. And we want to understand that we already visited the 1 node, and we know its entire component size, and there is no need to check it again. So even outside of our BFS function, we still want to have our visited set. So it's important that for this problem, our visited set is created here in the parent function and not in the BFS function. However, there certainly are times where you want it in the BFS function. So this is something that you should be careful about when you're implementing BFS. All right, now we can start writing out our get component size function. So we're going to take in a start node and we'll take in our graph. Then we will execute a pretty standard BFS here. So we're going to create a queue, which we will use an array for. We will add our start node onto the queue. Then, you know what? We're actually going to need our visited set here. I forgot that. So let's pass that in. Okay, we'll say so long as the queue is non-empty, So long as the length is greater than 0, we're going to do our 3 steps. We'll remove node, remove node, process node, and then add neighbors. Okay, now we'll say const node is going to be q.shift. And then here I'm going to leave a note. This you should always do in a real interview to mention that you know that this q.shift is suboptimal. We'll say the shift method is order n time, where n is the length of the array. The array. So in practice, we use a real queue data structure. So this is important. One, you should mention it to your interviewer because using shift is definitely not optimal and it changes the time complexity of your solution. But two, you should explicitly write this down because in cases like Google, your actual code is sent to hiring committee and your interviewer may not write down the fact that you mentioned this. And so you want it to be very, very clear, both your interviewer and to hiring committee, that you understand what is happening here in terms of the JavaScript methods, and you understand that, if you were working in a real code base, you should not implement it like this. All right, the process node step, we can come back to that, and we'll do neighbors here is going to be graph at node. There's also the case where something has no neighbors, and it looks like they will include that key in the adjacency list. So graph at node should always exist, so we don't have to do any sort of check to make sure that the node is in graph. Then we can iterate over each of our neighbors, and what do we want to do? Well, we can say if we've already visited the neighbor, and remember, visited right here is coming from a parameter. Now, if the visited set has our neighbor, we can continue. Then we can add our neighbor to the queue. Now, there's one other point. We're actually going to add the neighbor to our visited set immediately afterwards. And the reason is that we could actually double add to the queue if we don't do it right here. Because you can imagine that, suppose we have 5 and 8 in our queue. So you can imagine we kind of, actually that's a bad example. You know what, that's fine. Let's just say 5 and 8 are in the queue right now. First we process the 5 node, we add its neighbors, we add 0 to the queue. So 0 is in the queue, but we have not marked it as visited. I'm assuming that we don't have this line here. So then 0 is in the queue, but it hasn't been processed yet. But 8 is our next node in the queue. So when we dequeue 8, we're going to push its neighbors onto the queue, and we also push the 0 because we have not yet moved or removed 0 from the queue and marked it as visited. So we're going to mark things as visited as soon as we add them to the queue so that we never double add something to the queue. So it is slightly better to be doing it this way. Okay, so now we add this to the queue. So we're saying if the neighbor is unvisited, mark it as visited, add it to the queue. Now the process node is kind of the core logic for this problem. And so, or I guess for this function. And for this function, our goal is to get the component size. So one thing we'll probably want to do is create a component size variable. So we'll say cur component size is going to be 0, and we'll return it in the end. And to make sure we actually get an accurate cur component size, what do we want to do for every node? Well, for every node we see, every new node we see, an unvisited node, we want to say, hey, I just found a new node, increment my component size by 1. And the process node step answers the question of what do I want to do for every node? So for every node, we can simply say, do cur component size plus plus. And that should increment our counter for every node. Our BFS goes through everything in the current component. And then in the end, we return the current component size. Back here, we should be grabbing the cur component size and updating our largest component size. So hopefully everything should work. You can go ahead and test this and see how it does. There might be some bugs in there. All right, looks like it failed. Let's see, so test 0, 0. Okay, so this one, it failed. So 0 should go to 1, 5, 8, 8, 5. So these guys are all in the same component. Oh, okay, so mine is outputting 5 when it should be outputting 4. Let's see, so 0, 8, and 5. Let's see, why are we doing that? 5, 8. Let's just go ahead and console.log every node that we're incrementing for, so that we can see why we are doing this. And let's I'm gonna put an empty line every time we finish a component. So for the first component, we're doing 08150. Interesting. Okay. So the reason is because we are not marking the start node as visited. Because if we had written our visited.add statement here in the process node step, then we would have marked the start node as visited. But if we're putting it here, then we need to explicitly add the start node to our visited set right here so that we don't process it twice. That is the bug, I believe. Let's see if that fixes it. Okay, great. Looks like we're passing that. I don't know if run does anything. No. Okay. Yeah, so test should be fine. It looks like this solution works. That's all for this video, and thank you for watching.